Hello and welcome back. In this example we want to discuss how we can optimize the throughput in a continuous casting process in a steel mill. So this goes directly, if you have heard the other lecture, Numerische Modellierung der Prozesstechnik by Dr. Lenz. This is the same example as has been discussed there, and now we want to discuss it here again, but using the approach and methods that we have developed in this course with deep learning frameworks. So let's run through the example first and then go through how we can optimize this. So suppose you are an engineer tasked with optimizing a continuous casting production line in a steel factory. Right? So you have a conic supply vessel of molten steel. So somehow in a furnace you melt your steel, right? And then you need to transfer it to the production line that then makes the next step of the product for it. And this is then a big conic supply vessel that transfers it from the furnace to this production plant. Right? So this supply feeds the continuous casting line, and from our engineering point of view we need a throughput of about 6 tons per minute. We also need to change these conic vessels over so that the continuous casting plant can actually then work continuously, hence the name. So we need to incorporate a change over time, and for the system that we have or that we imagine, we have a 60-second window in which we can move to the next conic vessel. So this needs to be incorporated as well. So this is a general setup that we have. We have the conic or the truncated cone, right, with an outlet orifice, for example, at the bottom. And we require a throughput of about 6 tons per minute and the change over time of 60 seconds. So then we make a few assumptions about the truncated cone that we have. So for example, we can fill the cone with molten steel to about 2 meters height, and then we have a radius of the truncated cone of about 0.9 meters at the bottom, and they're at a height with the molten steel initially of 1.2 meters. The density of molten steel is about 7 tons per cubic meter. So what we need to do is then to optimize the radius of the outlet R, so the small r at the bottom, because this is then what determines how fast this conic vessel will empty. So what we need to do is that we calculate the emptying time with respect to this radius, right? And the radius of the vessel inside depends, of course, on the height where we are. Right? At the bottom we have R1, and at the top we have R2, and because the conic vessel has a linear slope, this can be represented by alpha y. So then we can calculate the volume of a thin slice as PR squared, dV as PR squared dy, and we can integrate this. So the volume of the conic, the truncated cone, is given by this equation. So that means that the total mass given by the density and the volume is 48,820 kilograms. So this is the amount of molten steel that is contained in that conic vessel. So we have our total mass now, and we have our required throughput. This is about 100 kilograms per second, and we have our change over time of 60 seconds. So that means that the emptying time plus 60 seconds is 488.22 seconds, given by the total mass and the required throughput that we have. Right. Now, the optimization task as engineer that we have is to find the radius of the outlet orifice such that the vessel is empty in this time frame of 428.2 seconds. So how do we model this? We make a few assumptions and we take a simple model, Torricelli's law. So from an engineering and physics point of view, that means that we assume laminar and continuous flow. We also ignore the viscosity of the molten steel, and of course we assume that the liquid is incompressible and also has uniform density. Furthermore, we also assume that the radius of the outlet is far smaller than R1 and R2, but you can see later on that this is easily fulfilled. So Torricelli's law is then given by the following equation: the velocity at the output orifice, square root of 2 times g times h, where g is the gravity constant. So we have the volumetric flow rate through the hole at the bottom, right? So this can be set as Q. Q is A times V with A PR squared, so the area and of the amount of molten steel that flows through this hole in the bottom. Meaning that the change in volume with time is the negative volumetric flow rate, right? And so if we put all of that in, we have minus A, the area of the outlet orifice, plus V, given by Torricelli's law. Right, so we have the change in volume from the slide before, and now we also have the volume from the truncated cone, right? So the volume, depending on the time, depends on the height, and because we have the area at the given height, and because we have a truncated cone, the area is not constant, but it varies given with the radius between R1 and R2. So the area varies of pi r squared, where r varies between R1 and R2, plus the height where we are in time. So this can be written like this. We have a constant slope depending on R2 minus R1 given by the initial height. Now if you put those two equations together, we end up with an ordinary differential equation for the change of height versus time is minus the area of the outlet orifice versus the slice inside the cone given by time plus the velocity at the outlet orifice given by Torricelli's law. Right? And now we put everything in there, so we have now our dependency on r squared. This is what we need to optimize, and you can see that we also have the square root of h in the numerator and h squared and h in the denominator. Right? So this is where we have our differential equation. So we can now put this in a little different order because we want to find the empty time, so we rearrange all the terms, separate by dh and dt, right? And we can rewrite this as the following equation. So the emptying time is 1 over r squared, where r squared, as you remember, is the quantity that we need to optimize, plus the following integral. And if you remember from the previous few slides, this needs to be equal to 428.2 seconds, right? So we want to choose R2 so that on the left we have 428.2 and on the right we have all the integral with r squared. So if you plot this for a given radius, it would look like this. So if you assume for a moment, this is not the final solution, but if you assume for a moment that the radius of the outlet orifice is 2 centimeters, then it takes about 1500 seconds, give or take, for this vessel to empty. So how do we go about in finding the solution for this? First option is to do this solve this integral analytically and then do the root finding approach that we'll talk about in a minute. Right, so you can solve this integral and you come up with this analytical solution. And now we require that t empty is 428.2 seconds. So we want to find the root of the function t empty minus 428.2 equals 0. You can use many methods, for example Newton's method for doing that, and if you solve that you end up with an equation that leads us to r is about 38.77 millimeters. We can also, and this is what has been discussed if you also have been visiting the lecture Numerische Modellierung der Prozesstechnik, you can discretize the differential equation and then do the root finding approach. Right? So we go through time steps and you then do a fixed point iteration for n time steps, step through all the heights based on the differential equation until the vessel is empty for a given radius, right? Or a given cutoff time in case we don't converge, right? And then we sort of try our way through this differential equation for different values of r, and depending on how fine we make the time steps and how fine we choose the steps in the radius, we will come very close to the analytical solution. The third option that we have, and this is what we want to discuss here in a bit more detail, is to use a solver. That is essentially another Python package integrated with PyTorch, for example, that solves the differential equation for us and then use the root finding methods like, for example, using Newton's method. So here we have the relevant code on the right where t target, this is our required time, or t empty as we've seen it before. H at t end, this is the height of the molten steel inside the truncated cone, the vessel, at the target time at 428 seconds, and of course this should be 0, and R0 is the, or RO is the radius of the outlet, this is what we want to optimize. Now we have a Python function on the right. We want to compute the height at the end, at T end, for a given radius RO of the outlet orifice. Then we step through this. First of all, you notice then, if RO is now our variable, we want to make sure that this is a torch tensor, because we need to keep track of the computational graph. So this is the first, if not as instance, code. Then we compute the area of the outlet orifice. This depends on the radius that we want to optimize, obviously, right? And then is the differential equation. This is a differential equation that we've seen before. We use h-clamp. This is a PyTorch one, so to ensure that the heights don't go negative, so that the differential equation doesn't go into unphysical territory, right? And then in the end, you can see that dh is essentially the same differential equation that we've discussed earlier, right? And then, if you see down there, ODA int, this is the package that solves the differential equation for us. And if we do this, it pretty much finds the same optimal orifice radius. And there's only like a few microns of steel left, and of course, in a realistic system, that's empty. Now we've discussed this in terms of Torricelli's law, right? And this is the differential equation that we have solved so far. There are a few complications if you were to do this in a realistic setup that you need to take into account. So for example, the velocity depends on the height, but also that changes with the height, with time. So the velocity also changes. So we need to sort of consider a bit the type of the liquid that we have, i.e. the viscosity of it. So just as to put a few values out there, water at room temperature has a viscosity of about 1. Molten steel has about 4 to 7. Right, so you can see that you would expect a slightly different behavior, and just to compare this to honey. Right, so this is a very different ballpark. So we assume that molten steel behaves almost like water, but not quite. Right? And then if you want to make this even more realistic, you have to consider that you may or may not always have laminar flow, but you also may have some turbulent flow or a transition in between. And then the orifice geometry plays a larger role. There's actually a standard norm for this use case, and if we compare the radius at the optimal, look for the optimal radius. Before we had used the example at 2 centimeters, right? And this is what the plot shows us here, right? You can see if we make the plot for a fixed radius, you can see that before we had the vessel empty at about 1500 seconds, and now we take much longer. If we actually then make some moderate assumptions about the geometry of the outlet orifice, but take the viscosity of steel into account, right? And if we still want to keep in the target time, you can see that before we had found the radius was about 38.77 millimeters, but if you take the viscosity into account and do a little bit more about the outlet orifice, is actually closer to about 50 millimeters.